Hello, everyone. My name is Aiza Camporedondo, and I will be discussing one of the subtopics of rotational dynamics we call moment of inertia. But before we proceed, I have something to ask. Have you ever tried to? Okay, have you ever tried to play on a mechanical merry-go-round in the park when you were a kid? Because if you did, you might have noticed that it was much easier to push the platform when it was empty. So, this observation can be explained by the concept of moment of inertia, which will be discussed in this lesson. Let me present to you our learning objectives. First, we need to define the moment of inertia. Next, we're going to determine the factors that affect a system's moments of inertia, and then differentiate the moments of inertia of single object and the multiple object system. Then we need to calculate the moment of inertia of various rigid bodies. But before we dig deeper on that, um, let's proceed to a more basic concept of moments of inertia. A rotation is any turning about a fixed point. The line through the fixed point of a rotating object is what we call the axis of rotation. So if this object is being rotated, you will notice that the axis of rotation is actually on the center of the object's orbit of where it is rotating. You might have also noticed that the axis of rotation, since it is on the center, it also has a fixed point. Therefore, the axis of rotation is not moving. Consider a man um, in a build up hammer truck. Okay, so right here, the object is the one being rotated. Thus, the object's location is the one being, that is being changing, or it changes. The locations of the ball or the hammer is changing. However, the man on the center is not. Therefore, the axis of rotation is the man itself, or the man is on the axis of rotation. Okay, and the one who is being rotated right here is the object. Okay. I want to emphasize that the axis of rotation is really necessary to be identified in getting the moment of inertia. Now, what is the moment of inertia? So, it is a measure of an object's resistance to rotational motion around an axis. Systems with a large moments of inertia are hard to rotate or to stop its rotation about an axis. Additionally, heavier object tends to have a greater moment of inertia. Also, the farther a mass element or an object is from an axis, the greater its contribution to the moment of inertia. Thus, both the mass and the radius relative to the axis affect the moment of inertia. Then we can conclude the moment of inertia can actually be calculated using the formula moment of inertia is equals to the mass multiplied by the radius squared. That is in the case of a point mass. Let's have an example right here. Calculate the moment of inertia of a very small ball with the mass of 0.1 kilogram in a uniform circular motion with a radius of 2.3 meter. Assume that the ball is a point mass. In this case, we're going to use the formula moment of inertia is equals to the mass multiplied by the radius squared. Then we're going to substitute all the value of the mass and the radius. Now, if we're going to calculate all this one, we're going to be arrive to the moment of inertia is equals to the zero it equals to 0.529 kilogram meter squared. Thus, we can conclude that the ball's moment of inertia about the center of the uniform circular motion is 0.529 kilogram meter squared. Another example right here. Let's calculate the moment of inertia of a point mass with a mass of 0.50 kilogram in a uniform circular motion with a radius of 4.2 meter. In this case, we're going to use, again, the moment of inertia is equals to mass multiplied by radius squared. And then we're going to substitute all the value of the mass and the radius. If we're going to multiply the radius by itself and then multiply the result to the mass, we're going to arrive to the answer 8.82 kilogram meter squared. And that would be the moment of inertia of the point mass in a uniform circular motion. Okay, that is in the case of point mass. However, what if there are several point masses? In that case, the moment of inertia contribution of each point mass can be added together to determine the moment of inertia of the entire system. Thus, for a system with multiple particles, the moment of inertia is equals to the summation of total number of particles, mass of the 8 particle multiplied by the radius of the 8 particle squared. Let's try calculating this problem. Calculate the moment of inertia for a system of 3 particles. So there are several point masses, 3 particles with the following properties. The first particle has the mass of 2 kilogram and the radius of 1 meter. The second particle has mass of 3 kilogram and the radius of 2 meter. And the third particle is the mass of 5 kilogram and the radius of 3 meter. Now, in answering this one, we need to list the given value first. After that, since we have here the given, we're going to use the moment of inertia is equals to the summation of the total number of particles. We have here the mass of the 8 particle multiplied by the radius of the 8 particle squared. And this formula can actually be expanded. So in this case, this is what we have here is the expanded version of this formula. Now, after that one, since we all have the given or the given value, we need to substitute this one to that formula. Now, 2 kilogram is multiplied by 1 meter squared plus 3 kilogram multiplied by 2 meter squared plus 5 kilogram multiplied by 3 meters squared. The one we're going to solve the radius first here, since it is in squared form. Now, 1 multiplied by itself is actually still 1. And 2 multiplied by itself actually 4, and 3 multiplied by itself is 9. Now, 2 times 1 is 2 kilogram meter squared. 3 times 4 is actually 12 kilogram meter squared. And 5 times 9 is 45 kilogram meter squared. If we're going to add all this value, we're going to arrive to the final answer, which is 59 kilogram meter squared. And that is the moment of inertia of those particles. Okay. Now let's try another problem. A mass system consists of four identical particles, each placed at the corner of the square given by the following coordinates. And this is in meter. So the coordinate x first and then the y coordinate. Then the first particle has the coordinate 0 and 0. The second particle has the coordinate 2 meter and 0 meter. And the third particle has the coordinates of 0 meter and 2 meter. And the fourth particle has a coordinate of 2 meter and 2 meter. Now, we need to find the moment of inertia of the system about the z-axis. Z-axis, if the mass of each particle is 3 kilograms. So, now, in the given, we need to list all the given value. For the mass, the particle 1, 2, 3, and 4 has the same mass, which is 3 kilograms. Now, the with right here, this is not the radius. This is a coordinate. So we need to still solve for the radius of each particles and the moment of inertia on the z-axis. Okay, we have here the list of the given value and the coordinates of those particles. And since since we are given the coordinates, we need to draw a graph. Okay, so here's the graph. We have here the x is in the horizontal plane and the y is on the vertical plane. Now, the first particle is on the x coordinate 0 and y coordinate 0. So we can conclude that the first particles is on the center of the graph. On the other hand, for the second particle, this is where we're going to graph the second particle. For the third particle, can you guess? Okay, so this is where the third particle is located. How about the fourth particle? Okay, so this is where the fourth particle is located. Now, you have noticed right here on the problem, the moment of inertia of the system about the z-axis. So the z-axis, and actually what it meant here, the z-axis is actually on the center of the graph. The center of the graph. So the z-axis is actually the axis of rotation. And the axis of rotation, as what I have stated earlier, is on the fixed point, or it is not moving. Thus, the particle 1, which is on the center of the graph and the axis of rotation, we conclude that it is not moving. And also, the gap from the the radius of the particle 1 in related to the axis of rotation is actually 0, since the particle 1 is on the axis of rotation. So the particle 1 has 0 meter for its radius. On the other hand, for the particle 2, we have, oh my god, it is already shown. For the particle 2, we have here 2 meter. Why? Okay, for in this case, because particle 2 has 2 meter gap from the axis of rotation, or on the center. And that is that is the same case with the particle number 3. Now, how about for the particle number 4? In getting the radius of particle 4, we're going to use the radius formula. In the case of z-axis, radius is equals to the square root of the x coordinate squared plus y coordinate squared. So, okay. This formula can actually be still used if we're going to, calculate this one. It is still, the answer is still the same. Now, we need to get the radius of the fourth particle. So we're going to use the radius formula for according to the z-axis as the axis of rotation. Now, the radius is equals to the square root of the x coordinate squared plus the y coordinate squared. Now, the fourth particle is equals to the square root of 2 meter squared plus 2 meter squared. Then 2 multiplied by itself is equals 4. Same thing right here. And meter times meter, that would be meter squared. So this is meter squared. We're going to add this one. We will get 8 meters squared. And since 8 meters squared is, is we still need to apply square root right there, going to crush this out, this squared. So we are left with 2.8 meter. Now this is the value of the radius for particle 4. Okay, so we have now all the given radius of the first, second, third, and fourth particle out of the coordinates. Okay, we can now actually solve for the moment of inertia using the summation of total number of the a particle and mass multiplied by radius squared. We're going to expand this one like what we did earlier. And here is the expanded formula. So, of course, the next thing we need to do is to substitute the given value to this formula. Now, you have noticed right here that this is 0. Since 0 multiplied by any other number is still equals to 0, then we're not going to include this one. We're going to, exclude that one out of the solution. Next is we're going to solve this one. Right here's the radius since it is squared. 2 multiplied by itself equals 4. 2 multiplied by itself equals 4. 2.8 multiplied by itself is 7.84. You will notice that the number of digits is increasing because we are not going to round that off yet, because rounding off should be on the last step for every calculation. Okay, so in this case, 3 times 4, that would be 12 kilogram meter squared. 3 times 4 is equals to 12 kilogram meters squared. And 3 times 7.84 is equals to 23.52 kilogram meters squared. If we're going to add all this value, we will get the moment of inertia is equals to 47.52 kilogram meters squared, or if we're going to round that off, that would be 48 kilogram meters squared. And that is and then we can conclude that the moment of inertia of the 4-mass system is 48 kilogram meters squared. Okay. So let's proceed to moment of inertia of continuous mass distribution. In this case, if there is moment of inertia contribution of each infinitesimal mass element, or dm, can actually be added together. But instead of using summation, we're going to use integration, since there are infinitely many mass elements right here. Infinitely mass element. Okay. The moment of inertia with regards to the continuous mass distribution can actually be calculated using the moment of inertia is equals to integral radius squared multiplied by the infinitesimal mass element. This formula can actually be derived to many more formula depending on the geometry of the body and the axis of rotation. So moment of inertia of the rigid body. I'm going to show you that later. The axis of rotation of the rigid body depends on how it is rotated. So actually I haven't attached a picture on the PPT. So I will just, show you in the screen instead. So right here, the axis of rotation of a rolling bottle. So since if you're going to imagine that this bottle is rolling, we can conclude that the axis of rotation is actually along along its central axis. Okay. The axis of rotation is actually along the central axis of this bottle. However, if we're going to use the bottle for a spin the bottle game, the spin bottle game. So its axis of rotation is actually perpendicular to the bottle and through its center. If you're going to use this bottle for a spin the bottle game, the axis of rotation is center, through the center of the bottle. So it is rotating like this, spin the bottle game. The axis of rotation is through the center. Okay. Let me show you more, more example, especially on the rigid bodies. Okay. Here are the moments of inertia of some rigid bodies with mass. So for thin cylindrical shell with the axis of rotation along the central axis, we're going to use the formula moment of inertia is equals to mass multiplied by radius squared. For thin cylindrical shell naman, with the axis of rotation through the center, we're going to actually, you can actually use this formula. But as for me, I more this formula can actually be derived to moment of inertia is equals to 1/3 mass multiplied by length squared. So in this case, naman, solid cylinder, with an axis of rotation along the central axis, we're going to use the moment of inertia is equals to 1/2 meter. No, not meter. Mass multiplied by the radius squared. For solid cylinder naman, axis of rotation through the center, we're going to use the formula moment of inertia is equals to 1/4 mass multiplied by radius squared plus 1/12 mass multiplied by length squared. For hollow cylinder naman, along with an axis of rotation along the central axis, we're going to use the moment of inertia is equals to 1/2 mass multiplied by r1 squared plus r2 squared. For hollow cylinder with an axis of rotation through the center, we're going to use the formula moment of inertia is equals to 1/4 mass multiplied by r1 r sub 1 squared plus r sub 2 squared is plus 1/12 mass multiplied by length squared. For a thin spherical shell naman with an axis of rotation along diameter, we're going to use the formula moment of inertia is equals to 2/3 mass multiplied by radius squared. For solid sphere naman along diameter, we're going to use the moment of inertia is equals to 2/5 multiplied by mass multiplied by radius squared. Lastly, we have here the solid rectangular parallel parallelepiped. I don't know how do you pronounce that, but if in this if this is the case, the axis of rotation through the center perpendicular to the face. This is the axis of rotation. Okay. The moment of inertia right there, we're going to use the moment of inertia is equals to 1 over 12 mass multiplied by a squared plus b squared. So the a is the, the height, and the b is the width. Either of the two. Hmm. Another tip, we in determining the axis of rotation of the rigid body, we need to identify for the fixed position. So, diba, I have, shown you later. I not later. I have shown you earlier that the the axis of rotation is actually on the fixed point. So, for example, if you're in the spin the bottle game, diba, spin the bottle game right here, and then this is how the spin the bottle game being, turned. So you will notice that the center of the bottle through the center is actually not moving or on this fixed position. So that is why the axis of rotation is through the center of the bottle. On the other hand, if we're going to, to roll this bottle, the rolling bottle, we can actually put this through right here. Along the center of the bottle is where the axis of rotation, and it is still on the fixed point. So, in determining the axis of rotation, you need to draw an imaginary line through the fixed point and perpendicular to the plane of rotation. Okay, so let's practice. Uh, Consider a 4.00 kilogram uniform solid cylinder is rotated about its central axis. If its moment of inertia is 0.218 kilogram meter squared, determine the radius of the cylinder. Okay, so we are not searching for the moment of inertia right here, but instead we need to find the radius of the cylinder. So in this case, we're going to use the moment of inertia is equals to 1 over 2 mass multiplied by radius squared, since this is in the solid cylinder. Now, we're going to manipulate all this this formula. Now we will get the formula. Radius is equal to the square root of 2 uh, 2 multiplied by moment of inertia over mass. Okay, so next is we're going to substitute all the given value to this formula. Will that leave us to 2? And the moment of inertia with 0.218 kilogram meter squared over the mass of 4.0 kilogram of the uniform solid cylinder. Now, in this case, if we're going to, multiply by 0.218 kilogram divided by 4.000, that square root, that will leave us to radius is equals to 0.330 meter. Why meter? Okay, so kilogram kasi, we're going to crush that out since there is, similar, what do you call this, unit. So we're going to crush that out. That leave us to meter squared. The square root right here will be, crushed out because we did the square roots. And that leave us with a unit of m for the radius. Okay, I guess, and I hope that you are, still with me. Okay. Okay, then um um we can conclude that the radius of the cylinder is equals to 0.330 meter. So let's try another let's make it simple and try another problem with the solid cylinder. So we're going to still use the formula earlier. So in this case, 5 kilogram 5.00 kilogram uniform solid cylinder is rotated about its central axis. So it is, rotated central axis, oh my God. Yeah. So if its moment of inertia is 0.369 kilogram meter squared, determine the radius of the cylinder. Still the radius. So in this case, I hope you know you know now how to actually get the radius of the solid cylinder, given that there is um, a formula. So in this case, you need to really manipulate the formula. So the moment of inertia is equals to 1 over 2 mass multiplied by radius squared. So we're going to exclude the radius right here because this is the value we need to find. Then square root is equals to 2 multiplied by moment of inertia divided by the mass. So we're going to substitute all the given value for the moment of inertia, 0.369 kilogram meter squared, and the mass, which is 5 kilogram. We're going to, multiply this one. That will leave us to 0.738 kilogram meter per meter squared. And then since this is we're going to divide this one. So kilogram is being crushed out. And that leaves us to 0.1476 meters squared. And in this case, this is not the final answer. The squared right here can be, neutralized by the square root right here. So in this case, we will get the radius of 0.384 meter. And that would be the radius of the cylinder. Okay, we're done. So, we need to sum all the key points of our discussion. So rotation is any turning of an object about an axis. And the axis of rotation is perpendicular line through the fixed points about which an object rotates. Also, take note that axis of rotation is on the fixed point, or it is not changing location. Okay, another one. Moment of inertia is an object measure of inertial resistance to changes in rotational motion about an axis. Another one, we have moment of inertia depends both on the mass and on the distribution of the mass relative to an axis. So this refers to the radius actually. Now, what is the moment of inertia formula again? That would be the moment of inertia is equals to the mass multiplied by radius squared. Next is the moment of inertia of a rigid body may vary for different axes of rotation. Next, we have here the key formula. I have said this earlier. For moment of inertia of a single point mass, we're going to use moment of inertia is equals to mass multiplied by radius squared. This formula can be used if there is only a single point mass given. For mass of inertia, moment of inertia for a system of discrete particles of, many. You're going to use this formula when there is several point masses that is given on the problem. So you're going to use summation right here. On the other hand, the moment of inertia of continuous objects, this formula can actually be used if there is a continuous mass distribution. We're going to use the moment of inertia is equals to integral radius squared multiplied by the infinitesimal mass. So, yeah. And this formula can actually be, derived derived to another formula depending on the body or the geometry of an object and as well as the axis of rotation. Okay, so that's it. And this is, the references I have collected. Okay, thank you everyone for listening. I hope you have a good day. Bye bye.